Hello, everybody. It's me again, Professor Ma. And this is basically a fast review for the sections we went through in the last couple of weeks. Okay. And if you think back, a lot of topic based on cross sections, cross sectional length or area cross sectional length, or if it's a solid, it's slider open and a cross sectional area. Okay. And let's start fast review. The first things remember you have to do is that to extract the distance between 2 points. If the points are horizontal, the line on horizontal line, then it's always the right hand coordinate subtract the left hand coordinates to guarantee the answer is positive, which will be the length or distance. And if we're comparing 2 points, one on top, one on the bottom, it's always the top points minus the bottom points. So this is the orientation work. And in general, if I have a formula equations with a curve, and if I want to know the height, the curve, the point, generic point that is height of the x-axis. So I will look at the y components in terms of the function in x. But if I want to look at the horizontal distance with the y-axis, okay, then I will give the y and solve the x coordinate. That's the part I want to find. Okay, so here we go. So we have first areas is integral of length, basically. So here are area that basically made up of vertical length, so we call this type 1. Okay, suppose I know the vertical length or the distance of each one of these strips, I call L of x. Then each one of these strips area is L of x times dx. And of course, I want to add all of them up, sum all of the dAs, and voila. Fundamental thing of calculus says, oh, that sum turns into integral of the formula of the length dx, the dAs. Okay, and this type of situation is what we call type 1. I know what the top function is in terms of x, the height, the bottom. So the distance between this top and bottom is f minus g, the height minus the low. And this is the second type. Okay, and this is where things are horizontal, stack horizontal. So then I know what the right-hand formula in terms of y is, and the left-hand boundary on this side of green, and in terms of y. So I use the principle of the right-hand point in y, subtract the left-hand point in y, the formula. Okay. And whatever y goes from. And these are the respective two different situations. Okay. And then this generalized into finding volume. Same situation. This is sort of like type 1. And the way we do it is, suppose I know how to slice these shapes like a piece, like a bread, and up and down vertical slice. I know how each slice and the cross-sectional area is, and that I multiplied by the thickness, I get the volume of that slice. I want to add up all the volumes, and the fundamental thing calculus is, oh, well, you integrate it. You integrate the area times that thing with the dx. You add up all the dv's, the same as integrating these. You get a volume. And so this is applications in this using these particular shapes. Like I have a function y to the whole x, so I know how high each point is. Given x, I know what the height is. And when I do the spin, the height f of x becomes the radius. And so it generates a circle of area pi r squared, pi f of x squared. Hence, the volume is the integral of pi f of x squared. That's what a of x is. Okay, I know the cross-sectional area. Now, if suppose I take this stack of salami and put it horizontal, as slabs horizontally, then I will multiply. Suppose I know the cross-section area in terms of y, and multiply by the increment of dy, and I get each slab, horizontal slab volume. I add all of them up, which is an integral, and that will get a volume. And so in particular, like for instance, volume of revolutions. Now I spin around the y-axis. Okay, if I know this boundary curve, this distance x distance, okay, r is horizontal distance, is the x coordinate, which in terms of expressed as in formula in y, and that will be the radius as it's spinning, and that the area for the a of y over here will be pi r squared. So it's the same formula, just in different directions. Okay. And here are two examples. One is type 1, example C, sort of type 1 spin by type 1 area, and then type D is kind of utilized spinning type 2. Okay, and notice in D, and the cross-section area is a ring. Okay, it's a washer. So this is also called a washer or this method. And finally, then we use the cross-sectional length, talk about fluid paresthesia of a plate. If I know the cross-sectional length, I multiply by dx, and that will be roughly how this little thin little white strips, the area of that is. Okay. And I take that, multiply by the depth, which is dx, the distance to the top. Okay, times rho is the fluid density. We're going to use water. Okay, I think of borders. You can find this on the net. If it is oil, you can check what's the density of oil, stuff like that. Water, you can check on the net. So it's a constant. Okay, and so then the other things we use cross-sectional area is, suppose I have a blob of waters. Okay, in some sort of containers. Okay, we're going to use water again. Okay, I know the cross-sectional area. Okay, and I'm going to set up here up and down as the x-axis, and then the cross-sectional area times dx. Dx is a little bit over here. There will be a slab of water, and we need to move that times the distance you're going to move. So the rho over here times the dv is the weight of that slide. Okay, the weight of that slide times dx, the distance you're going to travel. That's the work that needed for that slab of water. Then we're going to add them up, which is the integral. And these are the two shapes we use quite often in this type of problem. The first one is the in regards to the pressure of our plate, and again, we encountered this before, and to do with the Pythagorean theorems, or if it's a cone shape, we use similar triangles and proportional problem. Okay, so this is a summary of the things we did on basic lot of. Okay, and that's it. And